so-called Martingale. So for that, first we consider so-called conditional expectations, and we discuss certain properties of conditional expectation, because you have seen that by defining the discrete time martingale, we need the properties of conditional expectations. And then we have given one example of a martingale. Okay, and then we discuss about more important martingale, that is called the Doops martingale. That means if I give you say L1 or the integrable random variable, then if we define Mn, which is the conditional expectations of this integrable random variable given the filtrations Fn. So what is your Fn is given to you, and then this Mn, this is a martingale. Okay, so later on actually we try to show that as n goes to infinity, whether this martingale it converges or not, and if it is converges, in which sense. Okay, because in probability, so you have to give the mode of convergence, because there is a concept called convergence in probability, convergence almost surely, convergence in LP or LR. Okay, so that actually one needs to show it later on. So we are going towards that. Okay, so for that we need some preparations and some preliminaries for that, so I am going to do that. And not only that, by using the Jensen's inequality for conditional expectations, so what we have seen, that if I give you a martingale, one martingale, then we can construct many sub-martingale in particular. So what it says that if you have any say convex functions phi, then phi of xn, it is a sub-martingale. But if I give you a sub-martingale, then what I need that my phi, it should be convex, and not only that, it should be integrable also. Is it not? Then we can have the sub-martingale. Okay, so already you have seen that if xn is a sub-martingale, then minus of xn, it should be a super-martingale. Is it not? Or the vice versa. If xn is a super-martingale, then minus of xn should be a sub-martingale. Okay, so whatever the result is true for this martingale, sub-martingale part, and then you consider for the sub-martingale case in that in this manner. Okay, so today we'll talk about more on that. In particular, so you know some kind of stochastic integral. In particular, I want to define say integral over 0 to capital T, some y of some d of x. Okay, so that it makes sense, but we are not going to define that part. What I try to show here, that kind of the discretizations for that, means in a discrete sense, what will be the stochastic integral. Okay, so for that I need one definition, that is called the predictable sequence. Okay, so what is this? So already it is given to you that Fn, this is a filtration, it is given to you. Okay, be a filtration and a sequence of say random variable. Okay, I denote as h of n. This is for n running from n greater equal to 1 is said to be predictable sequence if my Hn is f of n minus 1 measurable. For n greater equal to 1. Okay, so Hn, this is f of n minus 1 measurable. That is why it is a predictable. Okay, that is the definitions of a predictable things. And now what I have, if I have some adapted process, say x, which is I denote as my xn. Okay, this is for n greater equal to 0. This is my adapted process. And then I have my h of n, which is my predictable process. Okay, so then I try to define, as I say, that kind of the discrete means integral form in a discrete setup. So what is that? I define that h dot x of n for n greater equal to 1. I am defining, this is the notation for definitions, that summation over m is equal to 1 to n h of m x of m minus x of m minus 1 for n greater equal to 1. So why it is the discretized form of the integral? Already you know that if you have something like that, no, suppose you want to define some h d of x, okay, say in the Riemann-Stinger sense. So then actually what you are doing, suppose this is my 0 to capital T, suppose. So then you are basically discretizing that. Okay, there is some differences for that, because for any time interval actually you can find out, no, you don't need to consider that it is in a left point, right point, in between any point actually it holds. But here actually what it says, that suppose I have a discretization from 0 to capital T, that is maybe say suppose I have my m is equal to 1 to n, then the one element something like that, it should be know that this is h of some tau I, and then the difference of d of x of tau I, which is basically x of tau I plus 1 minus x of tau I, and then you consider over the sum. So it is a similar kind of things I have. Okay, so as n goes to infinity, it may converge to there. But what I'm saying that this is kind of the discrete time version of my stochastic integral. Okay. Okay. So, and then I define that what about as n is equal to 0. So by definitions I am saying that h dot x at 0 is equal to 0. This is for n greater equal to 1, because otherwise it does not make sense, no. This is the difference I am having, and then h dot x at 0, so you just think of as a 0. So you can think of my y, which is the h dot x. This is a adapted process, the sequence which satisfies these equations, okay, or this equality. Okay, so what I'm saying, that if you have xn, which is a super martingale, and this hn, maybe I can write down as a theorem. Let x of n is a super martingale. Okay, and my h of n be a non-negative, predictable, sequence such that it is bounded. Okay, such that it is bounded, then the sequence h dot xn, okay, is a super martingale. So there is nothing special about the super martingale. In particular, if you look at say my xn, which is a submartingale, then we have the similar conditions. And if my x is a martingale, then this h dot x, it will be again a martingale. But so in that case, for martingale case, I don't need the condition that this non-negativity of my hn, because already you have seen like in the previous case, if you have a submartingale, then I need the convex function phi, and also it should be non-negative or the increasing. Okay, increasing things is there. But here actually you will see that since actually I am multiplied by hm, so if it is a super martingale or submartingale, there you have inequality. So if you want that similar kind of inequality, so then what you need? You need basically it should be non-negative, so that the inequality does not change if you multiply it by h of n. Okay, so let us prove it. Proof is simple. So see that this h dot n, this is fn martingale, fn measurable, is it not? h dot xn, this is fn measurable. Why this is so? Because if you look at the definition, this is h of m and then x of m minus x of m minus 1. This is f of measurable, and then it is sum over m equal to 1 to n, hence it is f of n measurable. Because my filtration f of n, these are the increasing sequence of sigma algebra. That means if my n is less than or equal to n, then f of n is a subset of f of n. So if it is fn measurable, then it automatically is f of measurable for f of m measurable for big M. Means if my m is greater than n. So in that case, you see from the definitions of my h dot x, then it is fn measurable. Okay, and not only that, for each or for every n, this is integrable. Okay, because my hn is bounded. Okay, and then you see that for every n, it is integrable. Okay, so the first two conditions it's satisfied. So only what we have to show, basically the third conditions. Third conditions means that whether it is a super martingale or not. Okay, so let us consider the expectation of, okay, I denote these things just for simplicity like y of n. Okay, so then y of n given f of n plus 1. Okay, sorry, y of n plus 1 given f of n. So then this, what is this? This actually I can write down expectations of what is my h of n plus y of n plus 1. So I can think of this is my h of n plus 1, x of n plus 1 minus xn, and then plus y of n given f of n. Is it not? Because y of n plus 1, it should be summation over I is equal to 1 to n plus 1. Then actually first you write down what happen when I is equal to n plus 1, and then the next is y of n. So now if this is the case, then what we know that the conditional expectation, it is basically linear, already we have seen. So then what I can write down, this is expectation of, and that I can write down expectation of h of n plus 1, x of n plus 1 minus xn given f of n, and then plus expectation over yn given f of n. Is it not? So now what I know that this h of n plus 1, this is fn measurable. Then I can use the property that, okay, if it is fn measurable, and so something like that, you have expectation of xy given some g, this is equal to x times expectation of y given g if my x is g measurable. So if you use this property here, then what I have from here, that this is h of n plus 1 expectation over x of n plus 1 minus xn given f of n, and then plus now y of n is fn measurable, so I can take out this is y of n almost surely. Is it not? So now what is these things? hn is positive, okay, it is given to you, and x of n plus 1 is a super martingale. That means what? That x of n plus 1 given f of n, that is less than or equal to x of n. Isn't it? Xn is bigger. So that means this part is negative. Is it not? So because of that, this part is negative. This implies, therefore, h of n plus 1 expectation over x of n plus 1 minus xn given f of n, this is negative. Is it not? So this part is negative. Now we have equality. So then what I can write down? So this implies expectation over y of n plus 1 given f of n. This is less than or equal to y of, because this part is negative and this is equal to sign. This is y of n almost surely. So what implies that is my h dot x n is a super martingale. So now if you look at the proof, let's say here I am using super martingale only here. Up to that, everything is fine. So now if it is a martingale, then this part actually 0, expectation of x n plus 1 minus xn given fn, this is equal to 0. So you exactly have y of n. Hence, for a martingale case, you don't need the condition that h of n is greater or equal to 0. Okay, non-negativity conditions you don't need. So only you need for the sub-martingale case you need, because for the sub-martingale, what I know that this should be positive, hence this thing is greater than or equal to y of n almost surely, and hence for a sub-martingale case, hence my h dot x, it should be a sub-martingale. Okay, so I can think of remark, or I think I don't need to give a remark, already you understand what is the things. Okay, so for supermartingale or for the submartingale case, I need the non-negativity conditions, or for martingale case I don't need any conditions. Okay, but this h dot x, it will be a martingale, supermartingale or submartingale according to that my xn. Okay, so let us recall. So why you are doing these things, actually in particular later on actually issue that if we have, so this n I have, this is our basically the deterministic, n equal to 1, 2, 3 and so on. But what happens if you have a stopping time? Okay, let me recall. Already maybe I don't know whether I have defined the stopping time previously. Let me recall. So suppose I am considering n, which is from omega to 0, 1, 2, 3 and so on, is called a stopping time if my n is less than or equal to n. This is my fn measurable, okay, for all n. So n is less than or equal to n, so stopping time means basically it is a non-negative integer valued, okay, random variable such that this happens. So this is a random variable now. So whenever n I was writing down previously, so that n it is only deterministic, but in this case it is now the random variable. Okay, so now we consider these things h of n. Okay, this is by definition. I am thinking that function over n is greater than or equal to n. So where n is my these things strictly greater than n, so n less than or equal to n I have. So then you see that this h of n is my f of n minus 1 measurable. Okay, so this hn is f of n minus 1 measurable, hence by definition it is predictable, and also it is bounded by 1, non-negative, okay, and bounded by 1. So if I use this thing n, then what I have that h dot for any adaptive process x, okay, this n, what I have, this is nothing but x of n minimum of n. This is nothing but, this one is basically minimum of n and n, okay, minus x of 0. This one is minimum of, this is the notation, n always n, okay, or hat type. So this is x dot n, this is nothing but x of n minimum of n minus x of 0, because of this definitions of h of n. And hence actually what we have seen that this is a martingale or submartingale, okay, accordingly if your x is a martingale or submartingale, is it not? So this one is a submartingale, that h dot n x, in this case n cap n minus x of 0, this is a submartingale. So that means what I can say that if you have any stopping time n, we define the stopped process. So I can make a stop process. So this is a super martingale or martingale if xn is a super martingale or martingale or sub martingale, is it not, this process? So this implies h dot xn, okay, is a super martingale or martingale, hence sub martingale also, if xn is a super martingale or martingale. Okay, so I can also add the sub martingale things. Okay, let us make one definitions. So like, so for any stopping time n, we define the stop process xn, okay, which is stopped at n. What is the definitions? As my xn, x small n, capital M of omega, this should be my x of n minimum of n of omega. Okay, so this is the stop process. So you see that if my n is finite almost surely, then this makes sense. Okay, so you can think of the, okay, so I have a stopping time n which is finite almost surely. Okay, so that I can define this stop process. So in view of the above discussions, what I can write down as a theorem form, already we have seen that h dot x n, which is nothing but x of n dot n minus x of 0, is it not? That is actually we have seen. So hence what I can see from here, that if xn is a martingale and n is a stopped process, so if x of n is a martingale and n is a stopping time, okay, so this is, I can think of finite almost surely. Okay, then my stop process x and t is a martingale. Okay, and not only that, hence it is a martingale, what I can have expectation of x n minimum of n, this should be same as whenever I put as n is equal to 0. So that means this should be my expectation of x0. This should hold for all n. Okay, so for a stops process, if xn is a martingale, then the associated stops process, it's again a martingale, and not only that, I have expectation of x n minimum of n is equal to expectation of x0 for all n. Sorry. So then next we will talk about, okay, so what we have seen that if my xn is a martingale, then what we know that expectation of xn is equal to expectation of x0 for all n. Okay, so this result, can we, so question is, can we extend this result up to a stopping time? That means, can I say that expectation of x of t, if t is my stopping time, capital T or some notations, can we say that expectation of x0, so I can something like that, for a martingale xn, we know that expectation of xn is equal to expectation of x0. Okay, so my question is, can we extend? Okay, so question, can we claim that expectation of xt, okay, is equal to expectation of x0 for a stopping time t? Okay, this is my question, and answer is no in general. Okay, so for that let us consider. So answer no in general. So since I am saying that in general, that means there are some possibilities where it may happen, and there are some possibilities where this result is not true. Okay, let us consider one example. So consider a coin toss experiment. Okay, consider a coin toss experiment. So what I denotes this xi, I am denoting this is the number of heads minus number of say tail. Okay, in first ith toss. So this is my random variable. I am defining xi. So you toss a coin, you toss a coin. Okay, so the xi, which is the number of heads minus number of tail in the first I tosses. Okay, this is my random variable xi. Then you check it. You check this xi. Actually, it's a martingale. Okay, always you consider a no fair coin. It's not the bias coin. The probability p is lies between 0 to 1, but may not be half. But here actually I'm considering that that the probability of coming head is half and probability of coming tail is half. That means it is a fair coin. Okay, so then you check it that xi, it's a martingale, and expectation of x0 actually is equal to 0. Okay. So now I define my t, which is infimum over all those I, such that my say xi is greater or equal to 5. Okay. So first time that it basically that the xi, it should be 5 first time. So infimum of I such that my xi is equal to 5. Then this t, it's a stopping time. Check yourself, because xi, you see that actually that t is less than equal to I, it should be f of I measurable. So now what is my expectation of x of capital T? You see that it is 5. Okay, but which is not equal to expectation of x of 0. So that means for any t, means for any stopping time t, in general we cannot say that expectation of xt is equal to expectation of x0, even if your x is a martingale. Okay, so then what kind of conditions I need? So in particular here you see this t, actually that expectation of t is infinite. Okay. Okay, so under what condition this will hold, that is actually given by so-called the optional sampling theorem. That is actually I am writing down as a theorem form. You will see one nice example for that. Optional stopping theorem. What it says that, let us first write down the concept. So let xn, this is a martingale, and n, which is a stopping time. Always with respect to given filtration. So I am saying now suppose that any one of the following conditions holds. So what is the condition A? That n is bounded, that is there exists say k positive, k1 positive, such that my n omega less than equal to k1 for all omega is in my probability space, and B, that n is finite almost surely, and xn is bounded, that is there exists my k2 positive such that mod of xn of omega less than equal to k2 for all n, and all omega is in my omega. Okay, and condition C, I am saying that expectation over n is finite and there exists a k3 positive such that the difference of the conjugative difference of xn, x of n omega minus x of n omega, this is less than equal to k3 for all n and all omega is in omega. Under this condition, if one of these three conditions hold, then I can say, okay, then I can say that expectation x of n, which is equal to my expectation of x0. Under these conditions, I can say that expectation of xn is same as my expectation of x of 0, where capital N is nothing but the stopping time. So now if you see this condition 1, 2 and 3, so proof, if you look at this condition 1, 2 and 3, so from here it is clear that for each cases my n is finite almost surely, because n is bounded, hence it is finite almost surely. N is finite almost surely, it is given to you, and expectation of n is finite. Now n, it is non-negative, expectation of n is finite, so n should be finite almost surely, is it not? Because if it is infinite with probability 1, then expectation cannot be finite for positive or the non-negative random variable. So for each three cases, condition is that n is finite almost surely. So I don't need only finiteness almost surely, but I need more also with respect to maybe other conditions or with respect to some conditions on my given Martingale xn. Okay. So since n is my finite almost surely, then I can talk about my the stopped process, which makes sense, is it not? So note that in all three cases my n is finite almost surely, and hence this xn, okay, is well defined. So what is my xn in this case? Basically x of xn of omega is basically x of n omega omega. Okay, this is well defined, and already what we know that xn is a martingale, that stopped process x of n minimum of n, it's a martingale. Is it not? The previous things actually we have seen it, and hence actually, so it is a martingale, that means it is integrable for every n, and not only that, I have expectation of x of n minimum of n, this is actually expectation over x0 for all n. We have already seen it, is it not? So now I'll consider three conditions. So suppose case 1, or so suppose A holds, That means what? That means my n of omega less than equal to k1. That is, n of omega is less equal to k1, is it not? For every omega, for all omega is in omega. So now if I choose, this implies for all n greater equal to k1, then what is my x of n minimum of n? This should be nothing but my x of n, is it not? For all n greater equal to kn, because n is less equal to kn from my given conditions. So that means my x of n minimum of n is equal to x of n. Okay. And xn is integrable. X of n, this is integrable. So this implies my expectation of x of n, this is same as my expectation of x of n minimum of, in particular for k1, I know, and this is same as, actually already we know that for n greater equal to k1, I have already from this part, this holds for all kn, this is my expectation over x0. So if my stopping time n, if it is bounded, then this part is fine, is it not? Okay, so let us consider case B. So suppose B holds. That means what? That here it is given to you that my xn, they are bounded, is it not? And hence actually I can say x of n minimum of n of omega, this is less than equal to k2 for all n, and all omega is in my omega, is it not? This part actually it solves n minimum of n of omega less than equal to k2, because n is finite, already it is given to you, and x of n is less equal to k2 for all n, it is given to you. Okay, so now you see that x of n minimum of n, this is converges to x of n almost surely as my n goes to infinity, is it not? So this one converges to xn, and this one is a sequence which is bounded, hence I can use my bounded convergence theorem. By bounded convergence theorem, what I can say, that expectation over x of n or expectation over x of n, which is same as my limit n goes to infinity, and this is nothing but my expectation over x0, is it not? So for bounded convergence theorem, if I use these things under condition 2, I can have my this part. Okay. So now suppose C holds. So in that case, what is that? They said that my xn means the consecutive difference of xn means xn minus x of n minus 1, that mod less than equal to k3. So what I know that xn minimum of n of omega, see this part actually I can write down x0 of omega plus summation over I is equal to 1 to n of n x of k omega minus x of k minus 1 of omega, is it not? Like as a telescopic sum actually I am writing down. So this implies mod of x of n over omega. If you consider the mod, then mod of these things, so I have less than equal to mod of x0 of omega, which is integrable. No, x0 is integrable because xn is a martingale, and plus I can take mod inside, and then the modulus, what I know that for each k, xk minus x of k minus 1, this is less than equal to k3, and then I have my k3, and then whatever I have n, number of n is basically minimum of n and n, hence I can also put less than equal to n, because my n minimum of n, this is always less than equal to n. No, because this is the minimum. So by definitions of minimum things actually I had. So that means what? Now you see this n, in your case C, it is given to you expectation of n is finite. That means n is integrable. So now I have this one is integrable, this one is integrable, k3 is constant, hence this part is integrable. That means it is L1 of omega. That is the notation. And x of n minimum n, this converges to x of n. So x of nn converges to x of n, almost surely I know. And then this part is integrable. So you can use the dominated convergence theorem. Okay, so what I can say, that expectation of xn, this is equal to limit n goes to infinity, expectation over xn cap n. So this is nothing but my expectation over x of 0. Is it not? So this is expectation over x0. So this sampling theorem says that if my stopping time, if it is either bounded or if it is finite almost surely, but my sequence xn, it is bounded, or if my expectation of n is finite and the conjugative difference of xn, it is uniformly bounded by k, then I can have expectation of xn is same as my expectation of x of 0. Okay, so let us give one example or one applications of this theorem. This is very nice example. Maybe you already know these things. So it's basically that that gambler's ruin. Okay, it is so when one gambler stop playing the game, so he has some strategy that if he wins all the coins or certain coins, or if he lose certain amount of this, certain amount of money, then he wants to stop the game. So then actually try to find out what will be the probability that the gambler is ruined, means he lose, and what is the expected duration of the game. Okay, that means the if t is your stopping time, we want to find expectation of t. Okay, so consider the example of gambler playing a fair game. Okay, so the gambler starts with capital 0 and stakes say $1 in every round. So he wins and loses with probability half in each round. Okay, so the gambler wins the game if say he or she earns say $B and is ruined or lost if he loses say $A. Okay, so the game ends. Which one is faster? When the gambler either wins or is ruined. So we want to calculate the two things. As I told you, what is the probability that you will ruin? The probability P that the gambler is ruined, and secondly I want the expected duration of the game. Okay, so how to make it? Maybe solution I can think of. What is this? Basically, if you think of my xi, which is the capital of the gambler at the end of round I, okay, then you will see that this xi either it increases or decreases by 1 in every round with probability half. Is it not? Xi is basically either it increases by 1 or decreases by 1 with probability half, because if he wins with probability and the with probability half, and so it will be $1 more, and if he loses then actually it will be less $1 with probability half. So xi, I am saying this is the capital of the gambler at the end of round I. At the end of round I. So you check xi, it's a martingale. Okay, and not only that, you see as I, because of this xi minus x of I minus 1, okay, this is always less than equal to 1. Is it not? So now I am considering, see, when this gambler reaches the boundaries, either he wins total $B or he loses A, that means minus A. You know, these are the boundaries. So I am considering this T, which is this number of rounds I. So if we denote by TB such that it reaches B, that means infimum of I such that xi is equal to B, and T of A, which is infimum of A such that my x of I is equal to minus A. Okay, and then T, so infimum of I such that my x of I is equal to B, and T of A, I am saying that infimum of I such that x of I is equal to minus A. Is it not? So these are the boundaries. And what will be my T? Because the gambler will stop playing if it reaches one of these. That means T is equal to minimum of TA and T of B. Is it not? T is equal to minimum of T and TB. So then expectation of T is finite. Okay, suppose it is finite. Actually, one can check it. Actually, it will be a finite. So later on, actually, we will see for my question T, what is the expected value of T. Okay, so suppose it is finite now, and then I can apply the condition 3 of my previous theorem. Is it not? So what it says that if P is the probability of ruin, then 1 minus P should be the probability of wins. Then what is my expectation of x of t? So this is nothing but basically the probability of P if my x of t is equal to A. So this is nothing but P times minus of A plus 1 minus P times of B. Is it not? That is the expected value of x of t. And so by optional stopping theorem, O ST. Okay, so optional stopping theorem. What I have, that expectation over xt is equal to expectation over x0, which is my 0. Okay, so this implies that minus ap plus 1 minus p times b is equal to 0. So from there I can get p is equal to b by a plus b. Okay, so the probability that the gambler will win is b by a plus b. Okay. Okay, so to prove the second part, we consider yi. So for part B, consider yi, which is my xi square minus I. Okay, so my claim, you check yourself that yi is a Martingale again. Y is also again a Martingale. Okay, so basically Martingale with respect to, I can think of xi. Okay, that means you consider the sigma algebra fi, which is sigma algebra denoted by x0, x1 up to x of I, and then you see this yi, it's a Martingale. And not only that, yi minus y of I minus 1, if you check it, then what it should be, that this is x of I plus I square minus I. Okay, and then minus this is x of I minus 1 square, then minus I minus 1. Is it not? Now if you check, these things should be less than equal to 1 plus mod of xi square minus x of I minus 1 square. Okay, and this should be less than equal to 1 plus 2 times maximum over a square and b square. A is b is given to you already in the strategy of your game, that if the gambler wins b dollar, then he will wins, or if he loses a dollar, then he ruins the game. So that means that for each I, yi minus yi minus 1, this is bounded, this is my k3. Okay, and hence by OCT, optional sampling theorem, what I have, 0 equal to expectation over y0, which is equal to expectation over y of t. And now expectation of y of t, this is nothing but expectation over xt square minus expectation over t. Is it not? Because this is yi is equal to xi square minus I. So you put capital T here. Now this is actually, what is expectation of xt square? This should be with probability p, and then x of t, it should be a. So this is p over a square, or it is with 1 minus p, because t should be either ta or tb, no, minimum of that part. So then it is 1 minus p, and then I have my b square and minus expectation over t. So this implies what I have, that expectation over t, this is equal to p of a square plus 1 minus p over b square. So now this is p, what is the value of p? P value of, already we got it, this is b by a plus b times a square, plus this should be a, 1 minus p is nothing but a by a plus b. Okay, times b square, and now you see that this is nothing but my AB. So expectation of t is AB, hence it is finite, and we have, using optional sampling theorem, that the mean durations of play is nothing but the AB. Okay. Okay. So later on we will talk about so-called the convergence. Okay, I have a martingale. say xt or x of n. So question is what happen as n large? So can I say that my xn converges to some random variable or not? Okay, so for that what we have to consider, there is called the upcrossing lemma and Martingale convergence theorem. So I can consider this is upcrossing. What is upcrossing? So now I have a say stochastic process xt. Okay, say t greater equal to 0. This is my adapted stochastic process. And now for any real number, a, b is in R with a is less than b, the upcrossing, the number of upcrossing of x across this interval a b, what is the supremum of the non-negative integer n, supremum of the non-negative integer n such that there exists a sk tk with s1 less than t1 less than s2 less than t2 and so on. This is less than t of n, for which that x of sk, this is less than or equal to a, okay, and this is still less than b is less than equal to x of tk. So that means if you choose graphically how it looks like, so this is suppose this is line say a and this is b, and now we have some kind of path here. Okay, so now here it is cross one point, here it is cross one point, here it is cross one point, here say it is cross one point. If you denote these things, okay, so this is my a, suppose, okay, this is with b, so that here actually you say that if I denote this s1, okay, so the value x of s1 is less than equal to a, and then suppose I am denoting this one is t1, so x of t1 is greater than or equal to b, and now suppose this is my t2, s2 I am denoting this is, and also this is bigger, no, I have these conditions, s1 less than t1 less than s2 less than t2 and so on, x of t2, okay, s2, this is less than equal to a, and then I have x of t2, this is also greater equal to b and so on. So what it says that the number of the maximum or the supremum of the non-negative integer n, okay, such that this is whole. So in this case you see the number of upcrossing is 2, okay, in this along this interval a to b. We denote this by u of small n, okay, of ab. So in this case, for this example, it is 2. So why this is important actually? What it says that if, okay, similarly you can define the down crossing. Here also down crossing is 2 actually, already we have seen it. Okay, you can define the down crossing, and not only that, so similarly we can define the down crossing. Okay, so observe that between two down crossing there should be at least one up crossing. Okay. Between two up crossing there is a one down crossing, and between any two down crossing there is an up crossing. Okay, so that means if I denote, this is my U, okay, so UAB, which is the up crossing, and if I denote the down crossing is my D of AB, what it says that UAB minus DAB, this is actually 1. Is it not? The difference will be, it will differ by at most 1, at most. So this is less than or equal to 1. And if DAB is finite, then UAB should be finite. So UAB and DAB both either finite or infinite, because between two down crossing there is a one up crossing, and between two up crossing there is a down crossing. So either they will be finite or they are infinite, because it is differed by 1. Is it not? So it is differed by 1. So the significance of this up crossing lemma is due to the convergence of a sequence. Okay, the convergence criteria of a sequence. So I am just denoting, stating this theorem. There is nothing to do with my probability or the random sequence and so on. Just you have a sequence of real numbers, say xn. Okay, this converges to a x. Okay, if and only if. So it may be extended real number. X may be, means it may be depend on minus infinity and plus infinity. If the number of up crossings, say U A B, this is finite for all A less than B. Okay, this is the, means in a real analysis one can think of. So basically what it says that if you see that it is going up, down, the fluctuations, no? So if you have infinite fluctuations, so it cannot convert this, no? Because it is going down to less than A and going to greater than A. So you can intuitively think, no? Because if you look at here, no? Intuitively, so this is my sequence xn, you can think of these are the things, no? These are the points and so on thing. So now xn converges to x. So if you have this number of up crossing or the number of down crossing, if it is infinite for any AB, then xn cannot converge, no? Intuitively at least. But one can prove it rigorously. So I just state this theorem. Intuitively it is clear. So number of up crossing or the number of down crossing by the sequence xn, if it is not finite, then xn cannot converge to extended real number x. Okay, so we'll use this idea to our case, in particular for the sequence or for the Martingale or the sub-Martingale case, and we try to show that whether xn converges to x almost surely or not. Okay. So let us discuss something. That suppose I have xn, this is a sub-Martingale. Okay, and A is less than B is given to U. So I define that Nj, which is equal to -1, okay, n of 0, and for k greater or equal to 1, what I am considering that n of 2k minus 1, this is infimum over m is greater than 2 of n of 2k minus 2, such that my x of m is less than or equal to a. So you know we look at this s1, s2, s1, s2, t1, t2 and so on. So here actually we try to find out in the same way. And then I put n of 2k this is again infimum over m. This should be n of 2k minus 1 such that x of m is greater than or equal to b. Is it not? So then this nj, they are stopping time. And on this set, n of 2k minus 1 less than m less than or equal to n of 2k, this is basically f of m minus 1 measurable. Why this is m minus, this event is m minus 1 measurable? Because these things I can write down, this is same as n of 2k minus 1 less than or equal to m minus 1 union n of 2k less than or equal to m minus 1 that complement. Okay, so now this is f of m minus 1 measurable, this m minus 1 complement is f of m minus 1 measurable, hence this is f of m minus 1 measurable. Okay, now I define my h of m which is equal to 1 if n of 2k minus 1 less than m less equal to n of 2k for some k. So in this set I am putting 1 and then 0 otherwise. Since this set is f of means this event is f of m minus k, then what I can say, this hm is nothing but my predictable. H of m is predictable. Is it not? Also it is non-negative and bounded. It is bounded. So what we have seen there, that h, and also what I can have for x of n of 2k minus 1, this is always less than or equal to a, and x of n of 2k, this is greater or equal to b. That means between times this n 2k minus 1 to n of 2k, xm, it crosses from below a to above b, and hm, which basically tries to take this advantage of this upcrossing. So what I am saying, that this implies between times n of 2k minus 1 and n of 2k, my xm crosses from below a to above b. Is it not? Because it is there. So if m is there, then actually it crosses a to b, and xm actually basically counts that upcrossing. hm is basically, this counts the upcrossing. So therefore, for every time an upcrossing is happening, then we can make a profit which is greater than or equal to b minus a, because it is from a to b. So I have that every time an upcrossing is completed, then we have the profit of which is greater than or equal to b minus a. And I define my u of n, which is supremum of k such that n of 2k is less than or equal to n. Okay, so this is the un, which is the upcrossing along this. So now in my definitions I have S1, S2, S1, S2, S1, T1, S2, T2 and so on. So now here I have this N2K but in terms of my K. Okay. So UN, which is the number of upcrossing up to my time n through the interval AB. Un is the number of upcrossing of the sequence xn up to time n through my interval A to B. Then we have this upcrossing inequality, which is given by the next lemma. What it says that if xm be a submartingale, then b minus a expectation over un, okay, or un ab, this is less than equal to expectation over xn minus a plus minus expectation over x0 minus a plus. Okay, so the expected value of this upcrossing un is again the random. Un is the random. Then this is b minus this is less than equal to this expected divided by b minus a. Let us prove it, and then I will stop it. So using this upcrossing lemma or upcrossing inequality, we will prove the Martingale convergence theorem. Okay, you will see. I denote my y of m, which is my a plus x of m minus a plus. So now you observe that xm is a submartingale, and hence xm minus a plus is a submartingale, because you can use this Jensen's type inequality, and from there this is that non is increasing and it is convex, hence xm minus a plus, this is a submartingale. And not only that, so this implies ym is a submartingale. Not only that, that the upcrossings over AB by ym, which is same as the upcrossing over AB by ym. Okay, so number of upcrossings by xm over the throughout the interval AB is same as the number of upcrossings over the interval AB by the sequence ym. And thus what I have, that b minus a un, this is less than equal to h dot y of n. Why this last inequality holds? Because for each upcrossing we have a profit which is greater or equal to b minus a, and for incomplete upcrossing, if there exists some incomplete upcrossing, which makes a non-negative contribution to the right hand side. Okay, so I have this inequality. I define my k of m, which is 1 minus h of m. So define. Then this k of m is again non-negative. It is bounded, is it not? And also predictable. So km is non-negative, bounded, and predictable. Thus, since my ym is a submartingale, then I can think of my k dot y, okay, n is a submartingale. Is it not? The previously already we have proved it. So this is a submartingale. So since this is a submartingale, what I have, this implies that expectation of k dot y over n, this is always greater than or equal to expectation of k dot y over 0, and this is by definition it is 0. So expectation of k dot n, this is equal to 0 for all n greater equal to 1. Is it not? So now I try to write down my ym minus y0. This part actually I can write down k is equal to 1 to m hk of yk minus 1, okay, and then plus summation over k is equal to 1 to m k of small k of yk minus y of k minus 1, because k is nothing but 1 minus hm, so I add these things, so I have subtract, and then I have, that is why minus y0, it's kind of the telescopic sums, and this is by definition nothing but this is h dot y m and then plus k dot y over m. Is it not? So this implies, if you look at expectation over ym minus y0, what is that? So this should be less than or equal to expectations of h dot ym plus expectations of k dot ym. Is it not? So now already we know that this part is greater or equal to 0. This part already we have seen it from here. Okay, so that means expectation over ym minus y0, this is greater or equal to what I have. This should be greater than or equal to expectation over h dot y over m. Okay, so from my previously whatever we have here, if you take that expectation, so this implies means from, maybe I can denote some star. Okay, so from star what I have, that b minus a expectation over un, this is less than or equal to expectation of h dot y of n, and this part is less than or equal to expectation over ym minus expectation over y0. This is less than or equal to expectation of, what is my ym? Ym is nothing but a plus xm minus a plus minus, so what is your y0? This is expectation of a plus x of 0 minus a plus, and so this is less than or equal to expectation over xm minus a plus minus expectation over x0 minus a plus. So at the end what I have, this implies expectation over un, this is less than or equal to, if I have b minus a expectation over xm minus a plus, okay, minus expectation over x0 minus a plus. Okay, so this is the approaching inequality. Okay, so from this approaching inequality, actually we try to prove it. So I told you that, okay, I need some finiteness and so on. Okay, because this is the number of approaching by the sequence up to time n. So as I said, that as n goes to infinity, if my expectation of these things is finite and un is basically positive, hence it should be finite almost surely. That means my right hand side should be finite. That means I need some assumptions on my given some martingale, so that this will be fine. Okay, so that is the next result I am going, that is called the Martingale convergence theorem, and then okay, so maybe next day I will talk about. So idea is basically I need some assumption. In particular, I will give you that suppose my xm is a submartingale such that supremum over m expectation of xm plus, that is finite. Okay, so that this part should be finite. Now I have u of n. Now you see that if you increase your n, then un it basically increases. No, un the sequence it increases because it is up to time n, and then if you consider up to time n plus 1, then there will be more upcrossing, is it not? So un is increasing. And suppose u infinity we denote, which is the for all sequence the upcrossing using my whole sequences. Sorry, and then you can use your monotone convergence theorem to show that expectation of u infinity this is also finite. Okay, that means u infinity, which is the number of upcrossing throughout your sequence xn or the whole sequence xn, that is finite almost surely. And as I told you that like for deterministic sequence, if you have some sequence of real number and if you look at the upcrossings, so it converges if and only it is finite. So you can talk about that. Okay, it has a limit. Okay, that means my x of n it converges to x infinity almost surely. That we will show it. Okay, this is the general idea, that you look at the number of upcrossing or the number of downcrossing and try to show that the number of upcrossing throughout my whole sequence, okay, it is finite. Okay, I stop now.